The pond does not announce its rules out loud, but they are absolute. Water yields to nothing with mass unless that mass understands the boundary where liquid pretends to be solid. At first glance, the surface is a thin mirror, reflecting sky, reeds, and the passing shadow of a bird. Then the impossible happens. A small insect lands and does not sink. Instead, the water dimples beneath it, bowing inward as if stretched by invisible fingers. The surface curves downward under each leg, forming 6 shallow craters that never break. The insect moves, and the dents glide with it, skating across the pond as though the water were a taut membrane pulled tight across an unseen frame. This is not lightness in the poetic sense. It is not luck. It is physics, exploited to its limit. The water strider lives entirely at the boundary between 2 worlds. Below lies a dense, light-absorbing medium that can drown an insect in seconds. Above is air, unpredictable and filled with predators. The strider survives by committing fully to neither. Its entire body plan is an answer to one question: how close can you approach a liquid surface without falling through it? The answer in this case is so close that the insect never truly touches the water at all. What it contacts is surface tension, the molecular cohesion that binds water molecules together at their boundary, forming a flexible but resilient skin. At the scale of insects, surface tension is not a metaphor. It is a physical structure with strength. Each water molecule is pulled inward by its neighbors, and at the surface, where neighbors are missing, those pulls create a tight network that resists penetration. To a falling raindrop or a thrown stone, this resistance is negligible. To an insect that weighs only a fraction of a gram, it can be the difference between life and immediate death. But surface tension alone is not enough. Many insects are light. Many still sink. The water strider succeeds because it does not merely rest on the surface. It distributes itself across it with extreme precision. Its legs are long far beyond what its body size would suggest, stretched outward like spars on a bridge. This increases the contact area without increasing weight, spreading the downward force over a wider patch of surface tension. Each leg presses gently, creating a depression rather than a puncture. The water bends but does not break. The shape of those dimples matters. The deeper the curve, the stronger the upward force pushing back against the leg. Balance here is mathematical. Too much pressure and the surface ruptures. Too little and the insect cannot anchor itself to move. Look closer, closer than the human eye can normally resolve, and another layer of adaptation reveals itself. The legs of a water strider are not smooth. They are coated in countless microscopic hairs, each one angled and structured to repel water. These hairs trap air, creating a dry buffer between leg and liquid. When a leg touches the surface, it does not wet. It floats on a cushion of air reinforced by surface tension. Water beads and rolls away, unable to climb the hair shafts. This extreme water repellency, known as superhydrophobicity, ensures that the insect never becomes waterlogged. A wet leg would increase contact in the wrong way, collapsing the delicate balance and dragging the insect under. Every movement the strider makes is calibrated to maintain that balance. When it pushes backward to propel itself forward, it does not kick down. A downward kick would spike pressure and tear the surface. Instead, the leg sweeps sideways, sculling across the surface like an oar skimming ice. This motion creates vortices beneath the surface, spinning rings of water that carry momentum backward. The insect surfs on the reaction force, sliding forward without ever breaking through. The pond becomes a track, and the strider becomes a skater, exploiting the same laws that let a needle float or a soap film stretch without tearing. One wrong ratio changes everything. Add too much weight for the available contact area, and the surface tension yields. Shorten the legs, and pressure concentrates. Alter the hair structure and water climbs, wets, and drags. The water strider exists within a narrow corridor of possibility. Evolution has shaved and tuned this design until there is little margin for error. Even the insect's body posture matters. Its center of mass stays low and evenly distributed, preventing sudden shifts that could overload a single leg and punch a hole through the surface skin. This precision defines its lifestyle. The water strider hunts on the surface, preying on insects that fall into the pond and struggle at the interface between air and water. A mosquito that lands poorly or a fly knocked down by wind becomes trapped by surface tension, unable to break free. The same force that supports the strider becomes a snare for its prey. Vibrations ripple outward when something touches the surface, and the strider detects them instantly. Its sensory system is tuned to minute waves, reading the pond like a map of invisible signals. Direction, distance, and size can be inferred from the pattern of ripples alone. The strider pivots, accelerates, and reaches the struggling insect before it either escapes or sinks. Predators watch this boundary too. Fish lurk below, sensitive to shadows and disturbances. Birds skim above, alert for motion. The water strider survives by exploiting the hesitation of both. To a fish, the surface is a barrier, distorting vision and limiting attack angles. To a bird, the insect is small, fast, and constantly moving across reflective glare. When danger closes in, the strider can do something that seems to defy intuition. It can leap. A rapid downward stroke of the middle legs briefly overwhelms surface tension, punching a controlled hole just long enough to launch the insect upward. In an instant, it transitions from surface skater to airborne escapee, leaving behind collapsing dimples and fading ripples. The same legs that normally avoid breaking the surface can violate it when necessary, demonstrating that the insect does not merely rely on surface tension. It commands it. Temperature adds another layer of complexity. Surface tension changes with heat. Warmer water has weaker cohesion, reducing the strength of the surface skin. In cooler conditions, the surface tightens, becoming more supportive. Water striders adjust behavior accordingly. In warm midday ponds, they move more cautiously, minimizing force and avoiding abrupt accelerations. In cooler mornings or shaded waters, they skate faster, taking advantage of the increased support. This sensitivity ties their daily rhythms directly to physical chemistry, not just biological clocks. Even reproduction is shaped by this boundary world. Mating occurs on the surface, where balance is precarious. Males must maintain stability while grasping females, and females must tolerate the added weight without sinking. Some species have evolved subtle structural differences between sexes to manage this load, reinforcing legs or adjusting body proportions. Eggs are often laid on floating debris or vegetation, anchoring the next generation at the interface where they will live and hunt. The water strider's existence exposes an uncomfortable truth about how humans perceive nature. What appears to be an open, featureless surface is, in reality, a complex mechanical environment with rules as strict as any solid ground. The pond is not empty space between air and water. It is a habitat defined by molecular forces, and the water strider is one of its most precise specialists. Every glide across the surface is a test that must be passed again and again. A damaged leg hair, a sudden gust of wind, a drop of oil that disrupts surface tension, and the equation fails. The insect sinks, its adaptations rendered useless in a medium it was never built to navigate. There is no redundancy here, no second-chance environment waiting below. Survival depends on staying exactly where physics allows. The dents in the water fade as the strider moves on, leaving the surface smooth once more. No trace remains of the invisible skin that held, flexed, and released. But for the insect, that skin is as real as soil is to an ant, or bark is to a beetle. It is ground that can vanish if treated carelessly. The water strider does not conquer the pond by brute force. It survives by reading the limits of reality and living precisely within them. At dusk, when the air begins to cool and the sharp edges of daylight soften into layered shadows, a shape appears that seems out of place in both time and category. It moves with the urgency of a bird and the scale of an insect, vibrating in place before a flower, as if tethered by invisible wires. Its wings are a blur, its body steady, its feeding precise. This is not a hummingbird, though the resemblance is immediate and unsettling. It is a moth, and it should not be able to do this. The air at this hour is anything but calm. Warm currents rise unevenly from sunlit ground, Cooler layers slide in from shaded vegetation, and tiny vortices form and collapse without warning. For most insects, this is hostile territory. Hovering requires stability, and stability requires predictability. Yet the hummingbird hawk-moth arrives exactly when the atmosphere is at its most chaotic and performs one of the most demanding feats of insect flight: sustained hovering without contact, without rest, and without error. The insect approaches a flower head on rapid wing beats, decelerating not by braking against the air, but by reshaping the forces that hold it aloft. Its wings beat at a frequency so high that individual strokes blur into a continuous hum, generating lift on both the downstroke and the upstroke. Unlike many insects that rely on brief bursts of lift followed by passive gliding, this moth maintains constant aerodynamic control. Each wing beat is adjusted in angle, timing, and amplitude, responding to airflow changes faster than the human nervous system could consciously register. Hovering is not stillness. It is continuous correction. As the moth holds position, its body remains remarkably stable, its head locked onto the flower while the background shifts and trembles. This stability is not achieved by rigidity, but by flexibility. Tiny adjustments ripple through the wings, altering the shape of the wake behind them. Swirls of air form and collapse in tight, repeating patterns, creating a pocket of lift that the moth continuously rebuilds beneath itself. The insect is not resting on air. It is manufacturing support from turbulence. The feeding itself demands precision. The moth extends its proboscis, a long, coiled tube that unfurls smoothly and inserts into the narrow opening of the flower. Landing would be slower and riskier. Petals can bend, surfaces can be slick with nectar, and predators often wait among blossoms for careless visitors. By feeding on the wing, the moth reduces contact time and maintains an immediate escape route. The entire maneuver takes place in mid-air, powered by muscles that contract and relax at extraordinary speed without overheating or failing. These flight muscles are a study in endurance. They operate using indirect attachment, deforming the thorax itself rather than pulling directly on the wings. This allows for rapid oscillation with minimal neural input. Once the rhythm is established, the muscles maintain wing motion through elastic recoil, recycling energy from one stroke to the next. The moth's nervous system does not need to command each beat individually. Instead, it modulates the pattern, fine-tuning force, and direction as conditions change. Messy air currents buffet the insect from all sides. A passing breeze nudges it sideways. Warm air rising from a sun-warmed stone lifts one wing more than the other. Insects without advanced control systems would wobble, drift, or be forced to land. The hummingbird hawk-moth absorbs these disturbances and answers them instantly. Sensors at the base of its wings detect changes in strain and airflow. Visual cues from the flower and surrounding environment provide a fixed reference point. The moth integrates this information in real time, adjusting wing motion within fractions of a second. The result is flight that appears effortless, but is anything but. This stability is the moment that should not exist. Insects are small. Small bodies are easily pushed around by air. Turbulence that would barely register to a bird can be overwhelming at this scale. Yet the moth thrives in it. Rather than fighting turbulence, it exploits it, using unsteady airflow as raw material for lift. The vortices shed by its wings interact with ambient currents, sometimes strengthening lift rather than disrupting it. Where other insects lose control, this moth finds opportunity. Energy demands are immense. Hovering flight consumes more energy than forward motion, and the moth must fuel it continuously. Nectar provides a concentrated source of sugars that can be converted rapidly into usable energy. The timing of the moth's activity aligns with the availability of these resources. Flowers open, release scent, and replenish nectar at specific times, and the moth's daily rhythm tracks these cycles closely. Its hovering ability allows it to access flowers that may not support landing insects, expanding its feeding options and reducing competition. Predators are never far away. Birds patrol the same airspace, and ambush predators hide among blossoms. The moth's speed and control offer protection. If threatened, It can accelerate instantly, converting hovering lift into forward thrust without the delay of pushing off a surface. Its flight path can change direction sharply, exploiting three-dimensional space in ways that confuse attackers. The same wing mechanics that allow precise hovering also enable rapid escape. There is irony in its appearance. The moth resembles a hummingbird not because it is mimicking one deliberately, but because evolution has arrived at a similar solution under similar constraints. Both must hover to feed, both must stabilize in turbulent air, and both face the same trade-offs between energy cost and maneuverability. The resemblance can mislead predators accustomed to associating that flight style with a larger, more dangerous animal. The illusion is not perfect, but it does not need to be. Hesitation is often enough. Thermal conditions shape its behavior further. As temperatures drop, muscle efficiency changes. The moth compensates by increasing wing beat frequency or adjusting stroke amplitude to maintain lift. Its ability to thermoregulate is limited compared to larger animals, but the heat generated by its flight muscles helps maintain operational temperature. Hovering itself becomes a warming behavior, allowing the moth to remain active in cooler air when other insects slow or stop. Migration adds another layer to its story. In some regions, hummingbird hawk moths travel long distances seasonally, crossing landscapes that vary dramatically in climate and airflow. The same flight control that stabilizes hovering allows them to navigate unpredictable winds during migration. They do not simply drift with air currents. They correct, orient, and persist, maintaining direction over distances that seem disproportionate to their size. Every feeding event is a calculation. The moth must balance energy gained against energy spent, exposure to predators, and time. Hover too long and risk increases. Move too quickly and nectar extraction becomes inefficient. The moth's behavior reflects this balance. It samples, moves, samples again, tracing an invisible route through the ecosystem that links flowers, air currents, and metabolic limits into a single continuous process. To watch it hover is to witness the edge of what an insect body can do. There is no margin for failure built into this system. Muscle fatigue, wing damage, or sensory error can be fatal. Yet the moth repeats this feat dozens of times in a single foraging session, each hover as precise as the last. It does not conquer the air by overpowering it. It survives by listening to it, responding to its smallest shifts, and turning instability into support. When the moth finally departs, the air closes behind it without a trace. No imprint remains of the forces it shaped and reshaped to stay aloft. The flower sways gently, untouched. The moment passes, easily missed, yet it represents one of the most refined expressions of insect flight. In a world where small bodies are at the mercy of moving air, the hummingbird hawk moth has learned not only to endure turbulence, but to live inside it. The air above the wetland is crowded, layered, and deceptively empty. To human eyes, it looks like open space, a gap between reeds and water where nothing permanent exists. But for insects, this volume is terrain, structured by currents, temperature gradients, and invisible traffic lanes traced by prey and predators alike. In this three-dimensional arena, chaos should rule. Small bodies move fast, reaction times are short, and collisions are lethal. Yet cutting through this apparent disorder is a hunter whose dominance is unmistakable. A flash of red streaks across the sky, stops abruptly, pivots, and accelerates again. The scarlet dragonfly does not merely fly in this space, it controls it. From the moment it leaves its perch, the dragonfly claims the air as territory. Its wings beat independently, not locked together like those of many insects, allowing it to generate lift, thrust, and torque in finely separated ways. This gives it access to maneuvers that resemble aerial combat more than simple flight. It can climb vertically, hover briefly, reverse direction, or bank sharply without losing speed. But flight mechanics alone do not explain its success. Many insects can fly fast. Few can hunt with precision at speed. The scarlet dragonfly's advantage begins with vision. Its head is dominated by compound eyes so large they appear to consume the entire face. Each eye contains thousands of individual visual units, each pointed in a slightly different direction. Together they form a near spherical field of view, with only a narrow blind spot directly behind the head. The dragonfly does not need to turn to see what is coming. Movement anywhere around it is detected almost instantly. Yet the true power of these eyes lies not just in coverage, but in processing speed. Dragonflies are tuned to detect motion rather than detail. A small insect crossing the background creates a distinct signal against the visual noise of waving grasses and shimmering water. The dragonfly's nervous system filters this information ruthlessly, ignoring irrelevant movement and locking onto trajectories that match the size, speed, and direction of prey. What emerges is not a picture of the world, but a constantly updating map of potential intercepts. This distinction matters. The dragonfly does not chase in the way mammals do, reacting moment to moment to where prey happens to be. Instead, it predicts. When a fly crosses its field of vision, the dragonfly calculates where that fly will be, not where it is now. Its body aligns not with the prey itself, but with the future point where their paths will intersect. This strategy minimizes correction, reduces energy expenditure, and increases capture success. In a medium where hesitation means losing the target, prediction is everything. The odds should be terrible. Hunting in 3 dimensions at speed introduces variables that multiply rapidly. Air currents shift unpredictably. Prey can change direction abruptly. Visual clutter interferes with tracking. At insect scale, reaction windows are measured in fractions of a second. Yet the scarlet dragonfly thrives because it simplifies the problem. By committing early to an intercept course, it reduces the need for constant adjustment. Its flight path becomes smooth and deliberate, even when the prey's motion is erratic. This control extends to the body itself. The dragonfly's wings generate lift on both the downstroke and the upstroke, maintaining continuous support. Its abdomen acts as a stabilizing mass, shifting subtly to counteract unwanted rotation. Small changes in wing angle create immediate changes in trajectory. There is no wasted motion here. Every adjustment serves a purpose, whether to maintain alignment with a predicted intercept point or to compensate for a gust of wind. The wetland provides both opportunity and challenge. Swarms of smaller insects rise from the water surface, drawn by humidity and warmth. They form loose clouds that shift and reform constantly. For many predators, such abundance would be overwhelming. For the dragonfly, it is an advantage. Multiple potential targets allow it to select prey that matches its optimal hunting parameters. It does not waste energy on insects that are too large, too fast, or flying at unfavorable angles. Selection is instantaneous, guided by evolved thresholds built into its sensory processing. Predators hunt predators here as well. Birds patrol above, alert to flashes of color and movement. Frogs leap from below, snapping at low-flying insects. The scarlet dragonfly balances aggression with awareness. Its eyes track not only prey, but also larger moving shapes that signal danger. If a threat approaches, the dragonfly can abandon and intercept mid-course, switching instantly from hunter to evader. Its flight capabilities serve both roles without compromise. Temperature influences every aspect of this aerial contest. Dragonflies are ectothermic, relying on environmental heat to power their muscles. In cool conditions, their reaction times slow, wing beats weaken, and flight becomes less precise. To compensate, the scarlet dragonfly engages in behavioral thermoregulation. It perches in direct sunlight, orienting its body to maximize heat absorption. Its dark pigmentation helps absorb solar radiation, warming the flight muscles within the thorax. Only when optimal temperature is reached does it take to the air in earnest. Once airborne, flight itself generates heat, allowing the dragonfly to maintain performance even as conditions fluctuate. This creates a narrow operational window during which hunting efficiency peaks. Within this window, the dragonfly dominates. Outside it, the air belongs to others. Reproduction is woven into this mastery of space. Males establish and defend aerial territories, patrolling invisible boundaries above water and vegetation. Intruders are intercepted and driven off through high-speed chases that test endurance and control. These contests rarely involve physical contact. Instead, they are displays of aerial superiority, with the loser forced away by superior maneuverability and persistence. Females entering the territory assess these performances, selecting mates that demonstrate the highest level of control. Egg-laying ties the aerial predator back to the water below. Females deposit eggs on or near aquatic vegetation, ensuring that the next generation begins life in a completely different environment. Dragonfly larvae are aquatic hunters, equipped with extendable jaws and a sit-and-wait strategy that mirrors the predictive hunting of the adult in a different medium. The shift from water to air during metamorphosis does not erase this heritage. It transforms it. The scarlet dragonfly's success reveals an important truth about complexity. The air is not chaotic by default. It becomes manageable when the right information is extracted and acted upon quickly enough. The dragonfly does not see everything. It sees what matters. By narrowing perception to relevant motion cues and committing to prediction rather than reaction, it turns an overwhelming environment into a navigable one. To watch a dragonfly hunt is to witness order imposed on apparent disorder. The intercept is clean, almost understated. There is no frantic pursuit, no visible struggle. The prey simply disappears into the dragonfly's grasp, as if the outcome had been decided long before contact. In a space where chance seems dominant, control emerges through specialization. When the dragonfly returns to its perch, wings held outstretched, the air resumes its restless movement. Insects drift, currents twist, and light shifts across the water. Nothing in the scene suggests dominance, yet the memory of that red streak lingers. In this layered, unstable world, air superiority is possible, even at insect scale. It belongs to those who can predict the future faster than it arrives. The forest clearing appears open and navigable, a corridor of air between trunks and leaves where insects move freely, guided by light and scent. Nothing signals danger. Then the air resists. A flying insect strikes something invisible and stops so abruptly that momentum folds its wings inward. The space that moments ago offered passage has become a barrier, a wall made not of matter in the familiar sense, but of threads so fine they dissolve into background light until contact proves their reality. The web of the golden silk orb-weaver does not announce itself. It waits, suspended between branches, transforming empty air into a functional structure. This transformation is the spider's true achievement. The web is not merely a trap. It is an engineered extension of the spider's body, built from a material that combines properties rarely found together in nature. Strength, elasticity, and adhesion coexist within a single filament. The golden silk orb-weaver manufactures this material internally, from liquid precursors, assembling a structure capable of stopping fast-moving prey without tearing itself apart. The scale makes the result difficult to comprehend. Inside a body smaller than a coin, chemistry and physics cooperate to produce one of the most versatile biological materials on the planet. The silk begins as a protein solution stored within specialized glands. These proteins are not yet silk in any mechanical sense. They are dissolved, unaligned, and fragile. Only when the spider draws the solution through its spinnerets does transformation occur. Narrow ducts force the proteins into alignment, while changes in ion concentration and acidity trigger molecular bonding. The spider does not weave silk by placing finished threads. It spins silk by assembling it as it exits the body, converting liquid into solid through controlled chemical and physical stress. The resulting thread is stronger than steel by weight, yet far more flexible. This combination is essential. A rigid material would snap under sudden impact. A purely elastic one would stretch without stopping prey. The orb-weaver's silk does both. When a flying insect collides with the web, kinetic energy spreads outward along multiple strands. The threads stretch, absorbing force, while their tensile strength prevents breakage. The prey slows, stops, and remains suspended, trapped not by brute resistance, but by controlled deformation. Stickiness adds another layer. The capture spiral of the web is coated with droplets of adhesive silk, each one a microscopic reservoir of glue tuned to remain effective across humidity and temperature changes. These droplets are not passive. They stretch as prey struggles, maintaining contact rather than snapping free. The glue contains hygroscopic compounds that draw moisture from the air, keeping it tacky even as conditions fluctuate. A dry day does not neutralize it. A humid night enhances it. The geometry of the web matters as much as the material itself. The orb shape distributes stress evenly, radiating force from the point of impact outward along spokes anchored to vegetation. The spider positions the web in flight paths where insects are likely to travel, often between trees or across open gaps where air currents funnel movement. The placement is strategic. Too dense a location and debris accumulates. Too open and prey density drops. The golden silk orb-weaver reads the environment, selecting sites where airflow, light and insect traffic intersect. When prey strikes the web, the air itself seems to betray it. The insect was flying freely, wings calibrated for open space, and then the medium changes instantly. What was once empty becomes a structured surface with mechanical properties. The insect's nervous system cannot adapt fast enough. Its wings beat against resistance that did not exist moments before. Struggles only deepen entanglement as adhesive threads wrap and tighten. Each movement pulls more silk from the web, increasing contact area and reducing escape options. The spider feels this through vibration. Its legs rest on radial threads, sensitive to specific frequencies. A leaf blown into the web produces a different signal than a trapped insect. The spider does not waste energy investigating false alarms. When the vibration pattern matches living prey, the response is immediate. The spider moves along the web with speed and precision, adding more silk to immobilize the prey before delivering venom. Predators watch from beyond the web as well. Birds learn to recognize the faint shimmer of silk in certain light, avoiding collision. Larger animals sometimes tear webs apart accidentally, forcing the spider to rebuild. This destruction is not catastrophic. Silk production is metabolically expensive, but the spider compensates by recycling material. It consumes damaged sections of the web, breaking down proteins and reusing them to spin new threads. Nothing is wasted. Temperature and humidity influence silk performance, and the spider adjusts accordingly. In cooler conditions, silk becomes stiffer. In warmer, more humid air, it stretches further before resisting. The golden silk orb-weaver's web design reflects these variables. Spiral spacing, thread thickness, and tension change subtly depending on environmental conditions. The web is not a static object. It is rebuilt regularly, fine-tuned to current circumstances. There is irony in how visible the spider becomes compared to its creation. The web disappears into the background until light catches it at the right angle, revealing a golden sheen. This coloration is not incidental. The silk reflects certain wavelengths of light that attract insects while remaining difficult for larger predators to detect. What looks decorative to human eyes functions as part of the trap. The web advertises itself selectively, visible to prey, less so to threats. The spider itself occupies the center or a nearby retreat, depending on species and time of day. Its body mass is small relative to the structure it controls. This imbalance highlights the central truth of the orb-weaver's strategy. Power does not come from size or force, but from material mastery. By externalizing function into silk, the spider amplifies its influence far beyond its physical dimensions. Egg sacs woven from silk extend this strategy into the future. Protective layers regulate humidity, temperature, and defense against parasites. Even at rest, silk remains the interface between the spider's biology and the environment. It is shelter, weapon, sensor, and scaffold. The web does not last. Wind, rain, and impact degrade it. Each night or morning, depending on species, the spider rebuilds, responding to changes in its surroundings. This repetition is not inefficiency. It is adaptation in action. A static structure would fail as conditions shift. A dynamic one persists. To watch a web catch prey mid-flight is to witness chemistry and physics cooperating seamlessly. Molecular bonds formed inside a tiny body translate into macroscopic effects in the world. Air becomes a wall. Motion becomes stillness. The golden silk orb-weaver does not chase, does not overpower. It reshapes space itself, converting invisible threads into a functional environment where survival is decided. The forest clearing remains open to the eye. Insects continue to fly, unaware of the boundary they may cross next. The web waits, silent and precise, a reminder that some of nature's most effective tools are not muscles or teeth, but materials engineered at the molecular level, spun patiently into place by an animal small enough to overlook. The branch does not move when the wind passes through the canopy. Leaves flutter, shadows ripple across bark, and light fractures into shifting patterns, but one slender shape remains perfectly aligned with the stem it clings to. It is not hiding behind the branch. It is becoming the branch. In a forest where survival is decided in fractions of a second, the stick insect does not run, leap, or strike. It waits, betting everything on the limits of perception. Predators do not experience the forest as a static picture. Their vision is tuned to change. Movement is the signal that matters most, because movement reveals intention, vulnerability, and life. Color, shape, and texture follow only after motion has drawn attention. The stick insect's strategy begins with this reality. Its survival is not built on speed or strength, but on discipline. It exists by refusing to announce itself. The forest canopy is an arena of constant disturbance. Wind shifts branches unpredictably. Sunlight flickers as clouds pass overhead. Insects crawl, fly, land, and depart in overlapping layers of motion. Against this background, stillness becomes camouflage. The stick insect aligns its body with stems and twigs, not merely to match appearance, but to match behavior. When the plant moves, it moves. When the plant rests, it freezes. The timing is precise. A delay of even a moment can break the illusion. This synchronization is not passive. The insect's nervous system continuously monitors environmental cues. Mechanoreceptors detect vibrations transmitted through the plant. Visual input tracks the rhythm of surrounding motion. When wind causes branches to sway, the stick insect responds with controlled rocking, mimicking the oscillation of vegetation. The movement is slow, deliberate, and directionally consistent with the branch itself. It is not random motion, which predators can detect as anomalous. It is patterned motion, integrated into the larger behavior of the plant. Color plays a role, but it is secondary. The stick insect's body may resemble bark, leaf veins, or dried stems, but coloration alone would fail without behavioral restraint. Many animals share similar colors with their environment and are still eaten. The stick insect survives because it understands, through evolution rather than awareness, that being seen begins with being noticed, and being noticed begins with moving at the wrong time. The odds are brutal because the margin for error is almost non-existent. A bird scanning the canopy does not need to identify every object. It looks for discrepancies. A twitch out of sequence, a silhouette that shifts independently of the plant, and attention locks in. Once motion isolates the insect from the background, its shape becomes irrelevant. A stick that moves like an animal is no longer a stick. The stick insect's body plan reflects this constraint. Long, thin legs distribute weight evenly, allowing it to hold positions for extended periods without fatigue. Muscles are capable of sustaining tension without continuous neural input, reducing involuntary tremors. Even respiration is subtle, minimizing abdominal movement that could betray its presence. This is existence optimized for patience. Feeding presents its own risks. Leaves are food, but chewing creates motion. The insect times its feeding to moments when environmental movement is already high, such as during gusts of wind. Mandibles work slowly, taking small bites to reduce visible motion. At rest, the insect may remain immobile for hours, prioritizing invisibility over intake. Energy balance here is delicate. Eat too aggressively and risk detection. Eat too cautiously and risk starvation. Survival lies in moderation, guided by timing. Predators exploit mistakes. Birds hop between branches, probing with beaks. Reptiles move slowly along trunks, tongues sampling the air. Insects patrol leaves, searching for protein. Each predator has a different sensory bias, but motion remains a universal trigger. The stick insect's strategy holds across these threats because it targets perception itself rather than a specific hunter. It does not need to know what is watching. It only needs to ensure that nothing worth watching happens. Reproduction introduces another challenge. Finding a mate requires movement, but movement invites danger. Some stick insect species rely on proximity rather than search, increasing the chance that individuals encounter each other without extensive travel. Others reproduce without mating through parthenogenesis, eliminating the need to move at all. This reproductive strategy is not a convenience. It is an extension of the invisibility principle. Fewer movements mean fewer opportunities to be seen. Egg-laying continues this theme. Eggs are often dropped to the forest floor where they resemble seeds. Ants may collect them, mistaking them for food items, and carry them into nests where they are protected from predators and environmental extremes. When the eggs hatch, the young insects emerge in relative safety. This relationship is not cooperation in the traditional sense. It is exploitation of perception once again. The egg looks like something it is not, and the ant behaves accordingly. Temperature affects everything. As ectotherms, stick insects rely on ambient heat to regulate muscle function. In cooler conditions, movement becomes sluggish, increasing the risk that necessary motion will be mistimed or poorly synchronized. The insect compensates by selecting microhabitats that buffer temperature changes, such as sun-exposed branches during cooler periods and shaded areas during heat. Even here, movement is minimized. Relocation is calculated, slow, and often completed during periods of high environmental motion. The forest is not a static backdrop. It is a constantly shifting mosaic of signals, and the stick insect must continuously recalibrate. A branch broken by wind changes the local pattern of motion. New leaves alter visual texture. Seasonal changes transform the palette entirely. The insect's success depends on flexibility within restraint. It must adapt its stillness to a moving target environment. Ironically, the stick insect's invisibility is most effective when it is surrounded by activity. Absolute stillness in a motionless environment can be conspicuous. It is the contrast that matters. The insect thrives in complexity because complexity provides cover. The more movement around it, the easier it is to hide by aligning with that movement. Chaos becomes camouflage. This strategy reveals something fundamental about survival. Power does not always favor those who act. Sometimes it favors those who wait. The stick insect does not dominate its environment. It yields to it so completely that it disappears within it. Its body becomes a question mark in the predator's visual field, unresolved and therefore ignored. When the insect finally moves, perhaps at night or during a strong wind, the motion is careful and measured. Limbs lift and place with precision. There is no urgency, because urgency is visible. Even escape is subdued. Rather than fleeing dramatically, the stick insect often relies on dropping motionless to the ground, becoming debris among debris. Once again, survival depends not on speed, but on the refusal to stand out. The forest continues around it, indifferent and relentless. Predators search, plants sway, light shifts. Somewhere on a branch, a life persists by doing almost nothing at all. The stick insect endures not by confronting the odds, but by making itself irrelevant to them. In a world where detection means death, it survives by mastering the art of not being detected. The forest understory darkens quickly as evening approaches, and with the fading light comes a shift in priorities. Diurnal birds retreat to roosts, the air cools, and shadows grow longer and more ambiguous. In this dimming world, shape matters more than color, and suggestion matters more than certainty. It is here, in this perceptual half-light, that the owl butterfly's most improbable weapon becomes visible. When its wings are closed, the butterfly is unremarkable. Browns and muted grays blend seamlessly with tree bark and dead leaves. Veins trace patterns that resemble wood grain. At rest, it is a fragment of the forest, ignored by eyes searching for contrast and motion. Then the wings open, and the illusion collapses into something else entirely. Two large dark circles stare outward, ringed and shaded to resemble eyes that do not belong to an insect. In an instant, the butterfly transforms from prey into question. The eyes are not real, but the reaction they provoke is. Predators do not see the world objectively. Their perceptions are shaped by urgency and risk, filtered through neural shortcuts honed by evolution. Many attacks are decided before conscious analysis can intervene. Movement triggers pursuit. Contrast isolates targets. Familiar shapes confirm identity. The owl butterfly interrupts this sequence. Its eye spots hijack recognition pathways designed to detect larger, dangerous animals. The predator hesitates, and in that hesitation, the butterfly survives. This is not intimidation through power. The owl butterfly cannot fight. Its muscles are not built for sustained speed, and its body offers little defense against claws or beaks. Its advantage lies entirely in time. The eye spots do not need to convince a predator that the butterfly is an owl. They only need to introduce doubt. Is this prey, or is this something else? That fraction of a second is enough. The eye spots are placed strategically. They sit on the wings where they are most visible during a sudden display, oriented to face outward when the butterfly is disturbed. Their size relative to the body exaggerates threat, suggesting an animal far larger than reality. Shading and contrast create depth, mimicking the curvature of a real eye. Some even include lighter highlights, exploiting the way predators interpret reflections as signs of life and awareness. This visual deception works best in the conditions where the butterfly lives. The forest floor and understory are visually complex, filled with overlapping shapes and partial views. Light filters through leaves unevenly, creating patches of brightness and darkness. In such environments, the brain relies heavily on pattern recognition to make rapid decisions. The owl butterfly inserts a powerful familiar pattern into this confusion. Eyes mean awareness. Awareness implies danger. Predators that hunt visually, such as birds and lizards, are especially vulnerable to this tactic. Their survival depends on avoiding encounters with larger predators. Attacking the wrong target can be fatal. Natural selection favors caution when uncertainty arises. The owl butterfly exploits this bias perfectly. It does not need to win a fight, it needs to avoid one. Even when an attack does occur, the eye spots can misdirect it. Predators often strike at the most prominent feature, aiming for the head. When a beak or bite lands on a wing instead, the butterfly gains another chance to escape. Wing damage is costly, but not always fatal. A torn wing can still support flight, especially over short distances. A crushed body cannot. The butterfly's behavior reinforces the illusion. When threatened, it opens its wings suddenly, revealing the eye spots in a rapid flash. The movement itself draws attention, ensuring the display is seen. Then, if the predator hesitates or recoils, the butterfly closes its wings and drops or flies away, returning instantly to camouflage. The sequence is precise, too slow, and the display is incomplete, too prolonged, and the deception loses urgency. Timing, once again, is everything. This strategy is psychological warfare at insect scale. The butterfly manipulates perception rather than reality, inserting false information into the predator's decision-making process. There is no physical escalation, no energy-intensive chase. The cost is low, the benefit potentially enormous. Evolution favors such efficiency. The eye spots also influence interactions beyond predator encounters. They may play a role in mate selection, signaling fitness through symmetry and clarity. Producing and maintaining these patterns requires developmental precision. Imperfect spots may fail to deceive predators and may also be less attractive to potential mates. In this way, the eye spots link survival and reproduction, reinforcing their importance across generations. Temperature and light affect the success of the illusion. In bright, direct sunlight, details become clearer, and predators can more easily resolve the deception. In dimmer conditions, the illusion strengthens. The owl butterfly's activity patterns align with this reality. It is most active during crepuscular periods when light levels are low but not absent. This timing maximizes both camouflage and the impact of sudden displays. The butterfly's life cycle reflects similar compromises. Caterpillars feed on specific host plants, often at night, reducing exposure to predators. During development, energy is invested not in speed or armor, but in wing structure and pattern formation. The adult emerges already equipped with its primary defense. There is no learning involved. The deception is innate, encoded in wing scales arranged during metamorphosis. Predators are not static participants in this evolutionary exchange. Some individuals learn to ignore eye spots, recognizing them as false signals. In regions where such learning is common, selection pressure may favor butterflies with more elaborate or differently positioned spots. Variation persists, ensuring that the deception remains effective on average, even if it fails occasionally. The system does not require perfection. It requires unpredictability. There is a quiet irony here. The owl butterfly's most defining feature is something it is not. Its survival depends on borrowing the authority of another animal's gaze. The eyes do not see. They do not think. They exist solely to be seen, yet their influence is profound, shaping interactions without ever engaging directly. When the butterfly rests with wings closed, the forest reclaims it visually. It becomes leaf and bark again, a background element in a crowded scene. The eyes vanish, and with them the illusion of threat. Only when danger approaches does the false face return, staring outward with borrowed menace. In a world governed by speed, strength, and numbers, the owl butterfly survives by changing the question. It forces predators to hesitate, to reassess, to doubt. That hesitation is its victory, not through dominance, but through misdirection, not through force, but through perception. In the thin margin between decision and action, the butterfly finds space to live. The forest floor at night feels heavier than it does by day. Moist air clings close to the ground, carrying the smell of soil, sap, and decaying wood. Leaves settle after sunset, and the frenetic motion of daytime insects gives way to slower, more deliberate movements. In this dim layer beneath the canopy, force matters more than speed. Here, mass is an advantage, and leverage decides outcomes. From the shadows emerges a shape that seems disproportionate to the body that carries it. A horn curves forward like a pry bar welded onto a living machine. The rhinoceros beetle has entered a world where strength is not symbolic, it is applied. At first glance, the beetle's body looks overbuilt. Thick armor plates overlap across the thorax and abdomen, forming a rigid shell that resists compression and impact. Beneath this exoskeleton lies a dense network of muscle packed into a compact frame. This is not a sprinter's body, it is a chassis. The beetle moves with deliberate weight, each step pressing into bark or soil with traction that lighter insects cannot achieve. When it stops, it does not wobble. When it pushes, the environment yields. The horn defines the beetle's identity, but it is not a weapon in the conventional sense. It does not pierce or slice. It does not inject venom. It functions as a lever, an extension of the beetle's body designed to lift, pry, and displace. In contests between males, the horn becomes the primary interface through which force is applied. The goal is not injury. The goal is removal. One beetle must physically relocate the other, forcing it off a tree trunk, branch, or feeding site. These encounters often take place on vertical surfaces, where gravity adds another layer of complexity. Sap flows attract beetles, concentrating resources in narrow zones. Males arrive, climb, and stake positions. When rivals meet, they do not circle or threaten from a distance. They make contact. Horn meets horn, or slides beneath the opponent's body, searching for purchase. The beetles brace their legs against the substrate, claws biting into bark. What follows resembles industrial work more than combat. Grip matters more than speed. The beetle, with superior traction, controls the interaction. Its legs anchor it in place while the horn applies upward force. Muscles contract in coordinated waves, transferring power through the rigid exoskeleton into the horn. The opponent resists, pushing back. But once balance is lost, recovery is difficult. The lifted beetle has fewer points of contact, less traction, and fewer options. With a final heave, it is tipped backward and falls, wings buzzing briefly as it drops into the darkness below. The absurdity lies in scale. This is heavy machinery behavior executed by an animal small enough to fit in a human hand. The forces involved are immense relative to body size. Rhinoceros beetles are capable of lifting many times their own weight, not because their muscles are fundamentally different from those of other insects, but because their structure allows them to apply force efficiently. Short limbs reduce torque loss. Thick cuticle prevents deformation. The horn redirects muscular output into leverage rather than motion. Speed would be counterproductive here. A fast shove risks slipping. A sudden movement could break traction. The beetle's movements are slow, controlled, and relentless. Each push builds on the last, increasing pressure until resistance fails. This is not a burst, it is sustained output. The beetle's physiology supports this style of exertion. Muscles are built for endurance under load, supported by metabolic pathways that supply energy steadily rather than explosively. Thermoregulation plays a quiet but crucial role. As an ectotherm, the beetle's muscle performance depends on temperature. Too cold, and contraction strength drops. Too warm, and endurance suffers. Nocturnal activity helps stabilize these variables. The cooler night air prevents overheating during prolonged exertion, while residual warmth stored in wood and soil keeps muscles functional. The beetle selects microhabitats that balance these factors, often choosing thick trunks that retain heat longer than exposed branches. Armor protects more than just the beetle's vital organs. During contests, bodies collide, scrape, and compress against rough surfaces. The exoskeleton distributes force across rigid plates, preventing localized damage. This allows beetles to push with confidence, absorbing impacts that would injure softer-bodied insects. The armor also provides anchoring points for muscles, increasing mechanical advantage. Strength here is not just about muscle mass. It is about how that muscle is used. Females observe these contests indirectly. They do not assess strength through measurement. They assess outcomes. A male that holds territory gains access to feeding sites and mating opportunities. The horn, therefore, becomes both tool and signal. Larger horns generally provide better leverage, but only when supported by sufficient muscle and traction. Oversized horns without supporting strength become liabilities, awkward appendages that reduce balance. Evolution fine-tunes this balance, favoring individuals whose horns match their ability to use them. Outside of combat, the horn still influences behavior. Navigating through dense vegetation requires adjustments. The beetle lifts and angles its head carefully, avoiding entanglement. Its movements remain slow and deliberate, minimizing the risk of getting stuck. This caution extends to flight. Rhinoceros beetles can fly, but takeoff is laborious. Wings must lift a heavy body and rigid horn into the air. Flights are purposeful and infrequent, used primarily to relocate between resource patches rather than evade predators. Predation remains a threat, despite the beetle's size and armor. Mammals, birds, and reptiles can overpower it if given the chance. The beetle's defense is not speed, but resilience. When threatened, it clamps down, tucking limbs close and relying on its shell to absorb blows. The horn can deter some attackers by complicating grip or presenting an unfamiliar shape, but survival depends largely on being difficult to handle rather than impossible to kill. Larval life tells a different story. Beneath rotting logs, larvae consume decaying wood, converting low-quality material into stored energy. This stage is slow, focused entirely on growth. The larva builds the reserves that will later fuel adult muscle development. By the time metamorphosis is complete, the adult beetle emerges with a body already optimized for force. The environment has been shaping this outcome for months, unseen. What makes the rhinoceros beetle remarkable is not that it is strong, but how it uses strength. It does not waste energy on unnecessary movement. It applies force only where leverage amplifies it. The horn is not decoration. It is engineering. The legs are not just for walking, they are anchors. The body is not streamlined for speed. It is reinforced for pressure. In a world dominated by fast hunters and fleeting opportunities, the rhinoceros beetle represents a different solution. It wins by being immovable until it chooses to move something else. Watching two beetles grapple is like watching a scaled-down construction site, where progress comes through incremental force rather than dramatic action. One pushes, the other yields. Gravity finishes the job. When the contest ends, the victor remains, adjusting its stance, re-establishing grip, and resuming feeding as if nothing extraordinary occurred. The fallen rival disappears into the darkness below, the outcome decided without blood or injury. The forest absorbs the event quietly. This is strength expressed through control, not speed, not aggression, but the ability to apply force precisely where it matters. The rhinoceros beetle does not dominate its environment by chasing it. It rearranges it, one deliberate push at a time, proving that even at insect scale, heavy machinery can exist, powered entirely by muscle and intent. Night reshapes the desert without changing its geography. Heat bleeds slowly from stone and sand, and the air settles into layers that carry sound and vibration more faithfully than light ever could. Vision becomes unreliable here. Shadows swallow edges, and distances dissolve into uncertainty. For most animals, darkness is a disadvantage that forces retreat or caution. For the black scorpion, it is a working condition. The night does not blind it. It clarifies the world into signals it understands. The scorpion emerges from beneath a rock or shallow burrow as temperatures fall into a narrow, usable range. Its body is low to the ground, legs spread just enough to maintain stability without lifting its mass into the air. Every contact point matters. Each foot touches the substrate with sensory intent, not merely to support weight, but to listen. The desert floor becomes an information surface, transmitting messages through vibrations too subtle for larger animals to register. Here, sound does not travel primarily through air, it travels through matter. The black scorpion is built around this reality. Its eyes are small and simple, capable of detecting changes in light but not forming detailed images. This is not a limitation. It is a declaration of priorities. Vision is unreliable in darkness, easily fooled by shadows and distance. Vibrations, by contrast, are precise. A footstep, a wing beat, the scrape of a leg against sand all generate distinct wave patterns. The scorpion's survival depends on decoding these patterns accurately and acting on them faster than prey can respond. Along the scorpion's legs are arrays of mechanoreceptors tuned to detect minute ground movements. These sensors do not merely register that something is moving, they capture direction, distance, and rhythm. A beetle walking produces a different vibrational signature than a cricket hopping or a spider creeping. Even wind-driven debris creates a pattern that the scorpion can learn to ignore. The desert may appear silent and still, but to the scorpion, it is alive with structured noise. Hunting begins with stillness. The scorpion pauses, legs braced, body motionless. This is not waiting in ignorance. It is active listening. Vibrations reach each leg at slightly different times and intensities. The scorpion's nervous system compares these inputs, triangulating the source. This process happens without hesitation or conscious evaluation. There is no searching, no scanning. The prey reveals itself by moving, and the scorpion's body aligns automatically toward the signal. When the scorpion advances, it does so slowly and deliberately. Rapid movement would generate its own vibrations, masking those of the prey. Control is essential. Each step is placed to minimize disturbance while maintaining contact with the ground. The scorpion closes the distance until the prey enters a critical zone, close enough that escape options narrow sharply. At this range, reaction time matters more than strategy. The strike is not what most imagine. The stinger does not lead, it follows. First come the pedipalps, the powerful pincers that clamp shut with speed and precision. This sequence is deliberate. Venom is costly to produce and not always necessary. By seizing prey first, the scorpion assesses resistance. Small or compliant prey may be subdued entirely through crushing force. Larger or more dangerous prey triggers the next phase. Only then does the tail arc forward, driven by muscles that have been held in reserve. The stinger delivers venom tailored to incapacitate rather than kill outright, interfering with nerve signals and muscle control. The timing is crucial. A premature sting wastes venom and risks missing. A delayed sting risks injury. The scorpion's sequence reflects millions of years of refinement, balancing efficiency against risk in an environment where mistakes are rarely forgiven. Darkness shapes this behavior at every level. Without reliable vision, the scorpion cannot afford uncertainty. Its confidence comes not from bravery, but from sensory specialization. Vibrations do not lie in the way shadows can. They propagate through the ground according to physical laws that remain stable regardless of light. The scorpion's world is defined by these laws, and it navigates them with ease. Predators of the scorpion face a similar challenge. Many rely on sight, making the scorpion difficult to detect. Its dark coloration absorbs light, blending into night shadows. When threatened, it adopts defensive postures that maximize reach while minimizing exposure. The tail arches, the pincers open, and the body remains grounded. Even here, vibration matters. The scorpion can detect approaching threats before contact occurs, often retreating into shelter long before danger becomes visible. Temperature adds another constraint. As an ectotherm, the scorpion's metabolism and reaction speed depend on ambient heat. Too cold and muscles slow. too hot, and dehydration and fatigue become threats. Night provides a compromise. The scorpion times its activity to thermal windows, where performance peaks. Rocks and soil retain heat after sunset, creating microclimates that the scorpion exploits. Its movements follow these thermal gradients as much as prey availability. Reproduction also unfolds in darkness, guided by touch and vibration rather than sight. Courtship involves careful positioning and signaling through the substrate, ensuring that both individuals interpret intentions correctly. Errors here can be fatal. A misread signal may result in aggression rather than mating. Precision once again determines survival. The young scorpions inherit this sensory world immediately. From their earliest movements, they rely on vibration detection to orient themselves. There is no learning period for vision that never mattered. The desert trains them from the start to listen through their legs. The scorpion's venom often draws human attention, but it is not the center of its strategy. Venom is insurance, not the foundation. The true weapon is information. By detecting prey before prey can detect it, the scorpion reverses the usual disadvantage of darkness. Where sight-based hunters hesitate, the scorpion advances with certainty. There is a quiet irony in this design. The black scorpion is most effective when unseen, operating in conditions that would cripple visually oriented predators. Darkness does not level the playing field, it tilts it decisively. The scorpion does not overcome blindness. It never depended on sight to begin with. As night deepens, the desert continues its subtle motion. Insects emerge, rodents stir, and the ground hums with faint activity. Somewhere between stones and sand, the scorpion listens, reading a map written in vibrations. When the moment comes, it moves with calm precision, clamps first, stings only if needed, and feeds without spectacle. In a world where vision fails, confidence belongs to those who perceive differently. The black scorpion hunts not by seeing the night, but by feeling it, proving that survival does not always favor the sharpest eyes, but the sharpest interpretation of what cannot be seen. The forest does not ease into the sound. It detonates. One moment the air hums with the usual background of leaves and distant movement, and the next it is saturated, vibrating with a chorus so dense that individual notes vanish into a single relentless presence. The noise does not come from one direction. It pours from every trunk, every branch, every layer of the canopy. The cicadas have arrived, and with them, an entirely different set of rules. This is not a song meant to be heard by human ears. It is a force applied to the environment. The volume overwhelms perception, flattening auditory space until distance loses meaning. Close and far sound the same. Location blurs. The forest becomes loud enough to erase detail, and in that erasure lies the cicada's defense. For most prey animals, survival depends on avoiding attention. Cicadas invert this logic. They do not hide. They announce themselves collectively, transforming individual vulnerability into statistical noise. Predators that hunt by sight or sound are confronted not with a target, but with abundance. The question is no longer which individual to attack, but whether attacking makes sense at all. The emergence begins underground, unseen and patient. Cicada nymphs live for years beneath the soil, feeding on the diluted fluids of plant roots. This diet is low in nutrients and demands efficiency rather than speed. Growth is slow, measured, and synchronized across vast areas. The timing is not accidental. It is coordinated through environmental cues such as soil temperature and seasonal cycles. When conditions align, millions of nymphs tunnel upward almost simultaneously. The surface erupts with movement. Nymphs climb vertical structures, shedding their final skins as adults emerge pale and soft, wings unfolding and hardening in the open air. For a brief window, they are extremely vulnerable. Birds, mammals, reptiles, and insects converge, feeding freely. Yet even here, the strategy holds. There are too many cicadas to consume. Predators eat until full, then stop. The majority survive not because they escape, but because they are surplus. Once hardened, the adults take to the trees, and the sound begins in earnest. Male cicadas produce calls using specialized structures called tymbals, stiff membranes on the abdomen that buckle inward when muscles contract and snap back when released. This action repeats rapidly, generating pulses of sound amplified by the cicada's hollow body. Each species produces a distinct pattern, tuned to attract females of its kind. The calls are not melodic. They are mechanical, repetitive, and loud enough to carry over long distances. Loudness is the point. A single cicada calling would be easy to locate. Thousands calling at once create an acoustic fog. Predators that rely on sound struggle to isolate one individual from the mass. Directional cues are overwhelmed. The brain's ability to localize sound breaks down when too many similar signals overlap. The cicadas exploit a limitation in sensory processing, turning their own conspicuousness into camouflage. Even visual predators are affected. Movement draws attention, but when movement is everywhere, attention fragments. Birds dart into the canopy, snatch a cicada, and retreat, but their success rate drops as targets multiply. The odds favor the insects. Losing one individual has little impact on the population. Losing time and energy has a cost for the predator. This strategy extends beyond emergence and calling. Cicadas fly clumsily, often colliding with leaves or each other. Precision is unnecessary when numbers absorb losses. Their wings are strong enough to carry them between trees, but not built for evasive maneuvers. Speed and agility would be wasted investments. The cicada's body reflects its role as a temporary, overwhelming presence rather than a long-term survivor. Energy allocation reinforces this approach. The adult cicada's lifespan above ground is short. It does not feed extensively. Its mouthparts can still tap into plant fluids, but reproduction is the priority. All available resources go into calling, mating, and laying eggs. There is no attempt to preserve the individual beyond this window. The species persists by ensuring that enough individuals succeed, not by protecting each one. Females navigate the sonic chaos using subtle differences in call structure. Amid the roar, they detect rhythms and frequencies specific to their species. This discrimination is precise, filtering meaningful signals from overwhelming noise. It mirrors the predator's difficulty in reverse. Where enemies are confused, mates are guided. The same soundscape that protects the cicadas also organizes their reproduction. Egg-laying marks the beginning of another long cycle. Females cut slits into tree branches, depositing eggs that will hatch and drop to the soil below. Damage to the tree is real, but usually temporary. In healthy ecosystems, the nutrient input from fallen cicadas and discarded exoskeletons enriches the soil, feeding microbes and plants alike. The emergence is not just a biological event, it is an ecological pulse, redistributing energy accumulated over years into the food web in a matter of weeks. The forest responds. Predator populations spike temporarily. Scavengers thrive. Soil chemistry shifts. Even plant growth patterns adjust to the sudden influx of nutrients. The cicadas do not merely survive the environment. They reshape it, overwhelming ecological systems through sheer presence. There is an irony in the cicada's apparent recklessness. Individually, they are fragile. Their wings tear easily. Their flight is awkward. Their bodies offer little defense. Yet collectively, they are resilient. By synchronizing life cycles and compressing activity into a narrow time frame, they reduce the effectiveness of predation. This synchronization is so precise that in some species it spans over a decade, ensuring that predators cannot easily adapt their life cycles to exploit the event. The should not exist moment is not the sound itself, but the idea behind it. Conventional logic suggests that being loud and numerous makes prey easier to hunt. Cicadas prove the opposite. When the world becomes too noisy, targeting fails. Attention fragments. Focus collapses. The environment itself becomes saturated, and within that saturation, individuals vanish. As the weeks pass, the sound fades. One by one, the callers fall silent. Bodies litter the forest floor, spent. Eggs wait quietly in branches. Beneath the soil, the next generation begins feeding, growing, and counting time in seasons rather than days. The forest exhales, returning to its usual rhythms, but changed in ways that are not immediately visible. The cicadas leave no monuments, no lasting structures, Their impact is temporal, explosive, and transient. Yet it is profound. They demonstrate that survival does not always require concealment, speed, or strength. Sometimes it requires scale. Sometimes the most effective defense is not avoiding detection, but making detection meaningless. In the end, the cicada does not defeat its predators through force or cunning. It defeats them through excess. By overwhelming the sensory systems that predators depend on, it creates a brief window where survival becomes probable simply by being one among many. In a world governed by attention, the cicada survives by destroying the very concept of focus. The forest floor of Madagascar is dense, cluttered, and unforgiving. Leaf litter piles into uneven drifts, fallen branches interlock like barricades, and the soil beneath holds moisture that turns every step into resistance. This is not a place for speed or elegance. Movement here is constrained, channels are narrow, and escape routes collapse without warning. For soft-bodied insects, this environment is a trap disguised as shelter. For the Madagascar cockroach, it is precisely the point. At rest, the cockroach is low and broad, its body flattened into a shape that favors contact over clearance. It does not rise above obstacles. It slides beneath them. Armor plates overlap across its back and sides, forming a segmented shell that bends without breaking. This is not a rigid casing meant to deflect blows at a distance. It is a structural system designed to absorb compression, resist crushing, and maintain function when pressed from above. In the understory, pressure is constant. Predators pin prey against the ground. Rocks shift. Logs settle. Leaf litter collapses under weight. The Madagascar cockroach survives not by avoiding contact, but by enduring it. Its low profile reduces leverage for attackers, making it difficult to grasp or pry loose. When pressed, the force spreads across the exoskeleton, rather than concentrating at a single point. The cockroach becomes difficult to control because there is nothing to grab. The exoskeleton itself tells the story. Thick, dark plates curve smoothly, minimizing protrusions that could catch or fracture. Beneath them, muscles are arranged to push outward against compression, maintaining internal space even when external pressure increases. The cockroach does not panic when confined. Its body is designed for confinement. Where softer insects collapse or rupture, it holds shape. Predators learn this quickly. A bird pecks and finds resistance. A mammal bites down and encounters armor instead of flesh. Even when captured, the cockroach resists manipulation. Its limbs press outward, pushing against the confines of a beak or paw. This resistance is not explosive. It is stubborn. The longer the struggle continues, the more likely the predator is to abandon the attempt in favor of easier prey. Then there is the hiss. When threatened, the Madagascar cockroach forces air through specialized openings along its body, producing a sharp, sudden sound. It is not vocalization in the traditional sense. There are no vocal cords. The sound is mechanical, created by rapid airflow interacting with body structures. The hiss is brief, loud relative to the insect's size, and unexpected. In the close quarters of the forest floor, it echoes sharply, startling predators accustomed to silence from invertebrate prey. This hiss is not meant to convince a predator of danger through sustained threat. It is designed to interrupt behavior. A moment of surprise creates hesitation. A predator loosens its grip or recoils just enough for the cockroach to press itself deeper into cover. As with many effective defenses, the hiss does not need to succeed every time. It only needs to work occasionally to be favored by evolution. The sound also serves another function. It communicates. In social contexts, hissing can signal disturbance to nearby individuals, prompting movement or readiness. While not social in the way ants or bees are, Madagascar cockroaches do aggregate, particularly in favorable microhabitats. Dense clusters provide shared benefits, including moisture retention and reduced exposure. The hiss, in this context, becomes part of a broader sensory language tied to survival in confined spaces. The environment reinforces these adaptations. Madagascar's forests experience periods of intense rainfall followed by drying heat. Flooding can collapse shelters, forcing insects into tighter refuges. During dry spells, humidity retreats into crevices beneath logs and stones. The cockroach thrives in these fluctuating conditions by remaining close to the ground and close to cover. Its cuticle reduces water loss, while its behavior minimizes exposure. It does not roam unnecessarily. It stays where conditions are buffered. Thermoregulation here is subtle. As an ectotherm, the cockroach depends on ambient temperature, but avoids extremes through microhabitat selection. The forest floor offers thermal stability compared to open air. Beneath leaf litter, temperature changes slowly, allowing the cockroach to remain active when other insects retreat. Its body mass relative to surface area further slows heat exchange, providing inertia against rapid temperature shifts. Reproduction reflects the same philosophy of protection and resistance. Eggs are carried internally within a robust structure, shielded from environmental stress and predation. Rather than scattering vulnerable eggs into the environment, the cockroach retains control until conditions favor release. Offspring emerge already adapted to confinement, immediately capable of pressing into narrow spaces and avoiding exposure. The odds against soft-bodied insects in this environment are severe. Predation pressure is constant. Physical hazards are everywhere. Control equals death. The Madagascar cockroach counters this by denying control entirely. It cannot be easily crushed. It cannot be easily gripped. It cannot be easily startled into panic. Its responses are measured, mechanical, and resilient. There is a quiet irony in how this insect is perceived. Cockroaches are often associated with fragility, with being easily dispatched. This species overturns that assumption. It is not fast, not venomous, not visually intimidating. Its power lies in refusal. Refusal to be shaped by external force. Refusal to collapse under pressure. Refusal to cooperate with the expectations of predators. Even locomotion reflects this resistance-oriented design. The cockroach does not leap or sprint. It pushes. Legs extend laterally, gripping substrate and forcing the body forward through gaps that appear too small to accommodate it. Compression is not an obstacle. It is a tool. The cockroach can flatten further when needed, sliding beneath barriers that stop bulkier animals. In captivity, this resilience becomes even more apparent. Attempts to restrain or manipulate the cockroach often fail not because of aggression, but because of structural integrity. It wedges itself against surfaces, distributes force, and waits. The strategy works in the wild because predators operate under time constraints. A struggle that takes too long is abandoned. The cockroach survives by outlasting attention. The hiss punctuates these interactions like a punctuation mark. Sudden, sharp, and decisive, it resets the encounter. The predator reassesses. The cockroach presses deeper into cover. Control slips away. What emerges is a picture of survival built not on escape, but on resistance. In a world that squeezes, crushes, and confines, the Madagascar cockroach thrives by being shaped for pressure. Its armor is not a shield held at a distance. It is a structure meant to be tested continuously. Its sound is not a warning of attack, but a disruption of intent. Its low profile is not stealth, but inevitability. The forest floor remains hostile, indifferent, and crowded with dangers. Soft-bodied insects perish daily, crushed by chance or captured by force. Among them, the Madagascar cockroach persists, moving slowly, fitting where others cannot, resisting where others yield. It survives not by controlling its environment, but by making control impossible. In the end, this is its greatest adaptation. Not speed, not poison, not deception, but endurance under pressure. A body designed to be pressed, confined and challenged, and to remain functional anyway. In a landscape that rewards resilience over brilliance, the Madagascar cockroach stands as a reminder that sometimes the most effective survival strategy is simply refusing to break.